everyone. Seeing that it's noon, let's go ahead and get started. Welcome to Socorro's webinar series, Coastal Observing in Your Community. Thank you so much for sharing your lunch hour with us. My name is Abby Wakely, Socorro's Director of Communications, and I will be facilitating and moderating the webinar. Socorro is hosting this webinar series to discuss, highlight, and raise awareness about coastal ocean observing activities in the Southeast U.S. Socorro is the regional coastal ocean observing system for North Carolina, South Carolina, Georgia, and Florida. We are one of 11 that make up the NOAA-led U.S. Integrated Ocean Observing System, also known as IOOS. Our mission is to sustain and promote observations that help keep you safe. This is a quick snapshot of the technology we support to accomplish our mission. Here are a few Socorro opportunities/news. Socorro and many partners are hosting a Drone in the Coastal Zone workshop for the Southeast and Caribbean next year. Registration will open soon. Our 2020 annual meeting will be held in St. Petersburg, Florida on May 18th and 19th. Information will be posted to our website as it becomes available. And lastly, our Giving Tuesday campaign is still going on. Consider donating today and help us give the gift of a student scholarship. We have raised 37% of the $15,000 needed. Any amount helps. All right, let's get to the reason you are all here, the webinar. All participants will be in listen-only mode. You are encouraged to type questions for the presenter or technical questions for me in the bottom right chat box. I will respond to them directly or post the questions to our presenter after his presentation. We're recording this webinar today and we'll be posting the recording on the Socorro website. We are very excited to welcome Dr. Peter Hamilton. He will be presenting What Do We Know About the Loop Current in the Gulf of Mexico from Recent Observations. Dr. Peter Hamilton has a 40-year career as a physical oceanographer with Science Applications International Corporation and its successor, Leidos Corporation. After retiring, he became an adjunct professor in the Marine, Earth, and Atmospheric Sciences Department at North Carolina State University. While at Science Applications International Corporation, Dr. Hamilton was responsible for data synthesis and interpretation of large numbers of current meter and other oceanographic and meteorological time series observations from many multi-year programs. Dr. Hamilton serves as a principal investigator for 3 major deepwater studies in the East, Central, and Northwest Gulf of Mexico, and has recently finished being a principal investigator and program manager for major observational and modeling studies of the loop current. And he has also recently finished being the program manager for a study of the deep Gulf circulation using Lagrangian floats. You can read the full bio on the Socorro website. Dr. Peter Hamilton, thank you so much for joining us. I am going to go ahead and promote you to presenter. You should be able to share your screen now, and you are unmuted.
Okay.
All right, I'm seeing your screen, and I can hear you just fine.
You're fine. Oh, thank you. Thank you, Abby. Yes. Our purpose today is just to talk about observations of the loop current that have been made in the last 10 years and have sort of advanced what we know how the loop current works. I'm not going to say anything about models. Modeling is very important, but models have to reproduce reality, and you only get to know about reality from observations. Just a minute. Oh, there we go. Okay, the loop current is part of the Atlantic Ocean general circulation of the western boundary current, which we know as the Gulf Stream, is actually part of that system, and its source waters come through the Caribbean and from the North Equatorial Current, actually the Brazil Current and other components of the Atlantic Ocean overturning circulation. So the loop current is just this part that comes in through the Yucatan Channel between Cuba and the Yucatan, makes a clockwise loop and then goes out through the Straits of Florida and then becomes the Gulf Stream along the east coast of the US. It's a very strong current, and it has lots of modes of variability. So this shows you sea surface height from altimeters, which I'll talk about later. But the black line is what we use to delineate the strongest current. So it is the 17 centimeter sea surface height contour, and it approximates where the strongest currents are. So it comes in through the Yucatan, as you can see there, and makes a clockwise loop and goes out through the Florida Straits. And there's generally a number of different formations of the loop current. The red area represents sea surface height high and warm water, and the blue areas generally represent sea surface height lows and cold water. The dots on the screen are actually a mooring array, which I'll discuss later. So in the top corner, we have a retracted strait where it goes from the Yucatan to the Straits of Florida with only a small loop. Sometimes it goes straight across, and then it becomes extended, grows into the Gulf, extending towards the Mississippi Delta often, but sometimes it can move over towards the West Florida shelf. Then it becomes unstable. You can see the large curvy meanders on the east side of the loop current, and then it sheds an eddy, and that eddy goes off into the Western Gulf, where it can be an important influence on the circulation there. So you can see the loop current will dominate the circulation of the Eastern Gulf and is an important component of the Western Gulf. One of the important results that has come from our recent studies is that there's a lot of energy below the loop current. Loop current we consider can go down to about 1,000 meters, but it's in 3,000 meters of water. So what goes on underneath the loop current, and when we started measuring this, we find that we get very high energies at certain times. And this is a representative of 4 years worth of deep float data which track water parcels. And you can see that what we call the energy, the kinetic energy, which is the variability of the currents, is very high under the loop current and stretching out towards the Mississippi Delta. That's on the on this screen. This screen is the mean flow kinetic energy, and you can see it's quite weak over most of it. There's some indication of flows around the boundary and in this gyre in the deepest part of the ocean, of the basin, and there is some indication of a mean flows under the loop current. Okay, when you look at, we looked at the loop current there, well, with altimeters. Altimeters have a limited resolution, so everything looks relatively smooth. But when you go to sea surface temperature, you start seeing rather more complex things going on, and a lot of variability around the boundary of the loop current, and in this case, a loop current eddy that is about to be shed. And we notice that there is small-scale frontal Campeche slope frontal eddies propagating up the Campeche slope. I've put the 200 and 2,000 meter isobaths on there, so you can see that most of those kinds of fluctuations occur over the Campeche slope, and then further we have cyclones developing along the front on the northern and eastern side of the loop current, and that has effect on the surrounding waters, so you can intrude waters onto the West Florida slope and onto the northern slope as well. So we move to transport through the Yucatan. This is really to show you that it is a two-layer system. So our friends from CICESE in Mexico maintained a line of moorings across the Yucatan Channel, and with a rather lot of instrumentation to measure the currents and temperature as well, all the way through for a couple of years. I think that series has been extended to like 4 years now. The current, these are isoplasts of speed, and you can see it's very strong towards the Yucatan shelf, maybe 2-3 knots, or maybe up to 4 knots up in this corner. Then it decreases with depth to about 800 meters or so, and is confined to the westward 2/3 of the channel. The gray areas are positive. That means it's flowing into the Gulf of Mexico, and the white areas are flows out of the Gulf of Mexico. And you can see that apart from this small area alongside Cuba, most of the deep flows are weak and flow out of the channel. The standard deviations are relatively weak compared with the means, except for in the corner, which is the meandering of the current primarily. So if you look at the total transport, we measure transport in sverdrups, which is 1 million cubic meters per second. And so that and we use the 6-degree isotherm as the bottom of the loop current, which is approximately around 800 to 1,000 meters in most places. You can see the total transport runs between 20 and 30 sverdrups, averages around 25 or 26. And if you look at the flow above the 6-degree isotherm, you can see it almost mirrors completely the total transport. And then the bottom transports, which is all these white areas, are quite relatively, 5 to 10, maximum 10 sverdrups out of the Gulf, and it fluctuates between going in and coming out. So it's a relatively small component of the transport, volume transport into the Gulf of Mexico. Now, all that transport goes out through the Florida Straits. Florida Straits has a depth limit of 800 meters. So that means, which is one of the reasons why we see most of the flow above 800 meters. Anything below that has a hard time getting out of the Gulf. So, what tools do we use to observe the loop current? I've already sort of illustrated some of the remote sensing. It's very important, and for a long time, satellite radiometers were the main source of studying the variability of the loop current, and they go back to the 70s. Lots of problems with sea surface temperature in that when it gets to summer, basically the contrast all disappears, and there's also a lot of clouds. The complement of sea surface temperature is ocean color, which measures generally the color of the ocean, of the surface ocean. And then the revolution was with the altimeters, which measure the sea surface height through a radar. And they're able to give you the sea surface height, and as I've shown in the original picture, you can see where the highs and lows are, and that tells you where the currents are going. So that's so we always use, particularly the altimeter, for getting the large-scale picture about what's going on in the loop current. The second one is drifters. We can deploy drifters at the surface and get their locations directly from the satellites through the satellite communications. And then we also have subsurface drifters, which we rely on sound sources which are placed in the ocean and then they listen to the sound sources and determine their location by that means. You don't get any real-time data from them. You deploy them, wait a couple of years, and then they come up, then they lose their ballast weights, come to the surface, and transmit all their data through the satellites to the lab. Similar to RAFOS or profiling floats of the Archive program, they're primarily to measure, again, they're autonomous, measure the temperature and salinity profile at specific points. But they're autonomous, so they just drift around with the currents, and then they profile at set intervals, give you a sort of random sample of the temperature salinity profiles. The ones we used in the Gulf of Mexico were parked at 1,500 meters, and they profiled every fortnight, every 2 weeks. And then the more traditional techniques are moorings. The picture is of the streaming of deep water mooring out of the back of the Pelican before dropping the anchor over the, well, you can just see the anchor behind the guy on the left. So moorings are fixed locations, and you measure currents, temperature, and salinity, and also other things. And then there is an instrument called a PIES, which is pressure-equipped inverted echo sounders, and they sit on the bottom, and they make acoustic travel times and bottom pressure and temperature measurements. And with some manipulation, you can get a lot of information from them. Okay, so let's go to the altimeters. So this is the ground tracks of the altimeters during the periods when we were making measurements. They all have different cycle times. So the red ones cycle every 10 days, the green ones every 17 days, and the blue ones every 35 days. And a lot of work has been done, particularly by Bob Lehman at CCAR, to be able, and people at Aviso, to able to map these single tracks, because it only measures the sea surface height along these tracks, and then you have to interpolate them into a map to get the whole picture. That's probably one of our most important measurements that that's done in a routine basis. So this is a sea surface height mapped onto a grid and shows the separation of an eddy. In this case, we call it Ekman, from the loop current. The dots again are a mooring array, and the black line is the 17 centimeter sea surface height contours. Notice the blue areas, the cold cyclones. These are cyclonic flows, which means that they're anti-clockwise. These are clockwise flows, and you'll see these blue areas popping up all the time, and they often interact with the eddies themselves, and in some cases can split an eddy into two, in the Western Gulf particularly. So the resolution of these maps is around about 50 to 100 kilometers, and maybe a week in time. So you don't see any small scale fluctuations in this data. All right, this is a movie, I hope, of a 2-year period running from January 2009 for about 2 years, and shows the separation of several eddies going on there. So this one was called Darwin, and it separates and moves off into the Western Gulf. The loop current did not retract very far, and it starts to grow again. Notice those cold cyclones at the head. and they start to move around the loop current, and then it separates, then it reattaches, separates again, and then again moves off into the Western Gulf. That eddy was called Ekman. And then the loop current begins to grow again. And again, you start to see the instabilities generating on the eastern side. And the cold then start to move around, and it starts to split off, and it reattaches again. In a minute, there it reattaches, and it reattaches again, and goes smaller, then it reattaches again, and eventually just about makes it into the Western Gulf before going away. And then we have another eddy coming we call Hadal or Hadal. And this one again shows the curvy meanders on the eastern side and splits off just about now. Just now, yeah. And that launches off into the eastern Gulf, a rather large eddy in that case. And then again, shortly after that, another eddy broke off, but again it reattached, and that's the end of that particular movie. So you can see how variable the loop current can be, even though the eddies, you've got 4 or 5 eddies detaching and separating in that time period. They're all slightly different. They have different configurations. Sometimes the loop current extended much further, and sometimes it didn't. But there are common features to the separation cycles. Okay, so let's look at in situ measurements from moorings. So this on the right-hand side, you can see a diagram of a sketch of a mooring for 3,000 meters of water. It has current meters, and then it has what was called an ADCP, an acoustic Doppler current profiler, which profiles the currents from its depth of 450 meters up to about 75 meters in the water column, with a measurement every 60 meters in this case. And then there are other time series measurements made with temperature, salinity, and pressure, temperature, salinity, and yes, that's mainly, and other currents at specific depths. And then on this side, this is the array that was deployed in US waters. So this particular mooring was deployed at C2. There are short bottom moorings in the deep places, and there are pies with the ones with the numbers, which I'll come to later. And then our friends in Mexico deployed an array across the Campeche bank in two sections, and there was part of an array from the Yucatan Channel. So these are all primarily measuring currents. So they measure currents every hour, and then we process them to try and understand what's going on. Okay, and then we have another in situ measurement, a pressure recording inverted echo sounder. It sits on the ocean floor at more than 2,000 meters of water, and it emits sound pulses at about every hour, and it measures the round trip travel times for acoustic pulses from the sea surface and back, and it also measures precision bottom pressure. You can use the round trip travel time as a proxy for vertical profiles of temperature and salinity using the historical databases to calibrate them. And it measures precision bottom pressure, and you also have near bottom currents from moorings, and it is used to define the bottom circulation. And it turns out that the the travel time is a very good proxy for what's happening above 800 meters, 800 to 1,000 meters in the water column. So you're going to be able to obtain what is called here the baroclinic pressure, just due to the upper part of the water column. And then with the bottom pressure and the currents, you can determine the circulation at the bottom. And then the total circulation is both of them added together. So you can see this is quite a bit stronger than the total circulation. It's because of the influence of these depth-independent currents, which we're measuring at the bottom. I'll come back to this point in a bit. And the other in-situ measurement are what we call RAFOS floats. They're acoustic floats. They're a long glass tube, which is precisely balanced to float at a particular depth in the ocean. They're equipped with hydrophones and temperature sensors, and they you have sound sources. We had 4 sound sources distributed throughout the basin, and they go off at certain times, and the float records precisely when it received the signal. And from some data processing, you can find out exactly where the location was. And they say they float around for 2 years in our case, and then they're programmed to drop their ballast weights, and they come up to the surface, and then they spill their guts to the satellites. So on the right-hand side, you can see all the tracks that were recorded by our program. I think there's something like 194 tracks for 2 years, a very long, dense data set. And this is the first time such a large data set's been obtained in the Gulf of Mexico. So we had ballasted most of them for 1,500 meters, which is below the loop current, and another smaller number at 2,500 meters. We did that because the sill depth of the Yucatan Channel is 2,000 meters, as you saw from the profiles. So the 1,500 meters had a chance to leave the Gulf, but the 2,500 meter ones we expected to stay within the Gulf. As it turned out, none of the floats we deployed left the Gulf. None of them left the Gulf through the Yucatan Channel. Okay, and then the in-situ measurements, Argo profiling floats. In this case, they're producing salinity temperature, which we call CTD, profiles to 1,500 meters. And basically, there were 7 floats and some other floats deployed. And over a 4-year period, in this case, they were taking random samples. And you can statistically, with the help of the altimeter, you can statistically analyze them to look at what only the floats that profiled in the center of the loop current or in the center of eddies. And so this is a typical profile you might see in the center of the loop current for salinity, temperature, and density. And what is most noticeable is that there is a strong salinity maximum at about 150 meters, and a salinity minimum around 800 meters, and a very weak density gradients below 1,000 meters. When we plot salinity against temperature for all these plots, all these positions, we find that below 16 degrees or so, the temperature and salinity are very tightly correlated. And if you know the temperature, generally speaking, you know the density and the salinity. And you can see the subtropical underwater, what we call is that salinity maximum, which characterizes a loop current. So when an eddy gets into the Western Gulf, we can determine if it's loop current water, not precisely whether there is a salinity maximum exceeding 36.5 0.5 particle salinity units in this region, and we can also trace the other water masses. This is called the Antarctic intermediate water, which an indication is that you have water from the Southern Ocean coming into the Gulf of Mexico, and then the one at the very bottom is called North Atlantic deep water, which has very little variability, and that comes from, as it says, from the North Atlantic deep waters. So we had at least 75 profiles in loop current or loop current eddy waters. These things, as it says, they're not guided in any sense. They stay at 1,500 meters, so the currents at 1,500 meters tell you where they're going to pop up. So let's go to the studies. The recent deep Gulf observations in the last 10 years were all funded by the Department of Interior. So we had the loop current dynamic study, which is the one to the right, one to the left, sorry, which was in the water for 2.5 years, which I've already showed the map. The purple line there is the mean loop current for the 2 years. And then we had the deep float study, which shows you how dense the float tracks are in the Eastern Gulf. The purple ones are in 1,500 meters, and the red ones at 2,500 meters. As I say, we had 194 float years of location data. And in this case, the darker colors represent currents that are greater than 15 centimeters per second. So that's one of the reasons why you see such energetic deep flows under the loop current and in the eastern basin. Okay, so let's go to some of the results. For the Moorings study, which is basically the arrows, this area here where the arrows are. Well, let's go back to the bottom timeline there. What we're plotting here is the area of the loop current and the area of the loop current plus an eddy. The blue line is the area of the loop current, which would be this inside this thing, and then you add on the area of the eddy. So it tells you when they separate, and both Ekman and Franklin had many attachments and reattachments before they escaped into the Western Gulf. Hadal only had one detachment before it completely separated. So you can see in this one here, this tells you the depth of the 6-degree isotherm. So it's warm when the loop current is extended and it goes cold, and it gets warm again and goes cold, etc. And then the most important thing is that the energy in the deep currents, this is all the deep currents, this is the 100 meters off the bottom in water depths greater than 2,000 meters, and all added up together. And this is the fluctuation energy, the variability, if you like, different frequencies. So, and you can see that just before or during the period of the separations and detachments, there is a huge increase in kinetic energy over 3 or 4 months. Similarly for Franklin, had a large increase, and for Hadal, similarly, we had a large increase, either just prior to or during the separation events. The timing seems to be related to exactly where the mooring array was relative to the separation. But still, the indication is that we have these periods of maybe 4 months where you get high energy in the deep. The black line is for fluctuations that are longer than 40 days. The gray is longer than 20 days, and the red is longer than 2 days. So most of the energy is at long periods, long period fluctuations. So we have these 4 months intervals of huge transfer of eddy fluctuation energy to the deep, under the loop current, but this compares with the length of the loop current eddy shedding cycle, which is on average 9 to 11 months. So it's probably less than half of the loop current eddy shedding cycle when you see these high energies at depth. These are from current meter moorings. When we go to the RAFOS velocities, what I did here is divide the loop current region into 3 regions: under the loop current, to the northeast in the basin, and then to the northwest south of the delta. And again, this is the picture of the area of the loop current and the area of the eddy. This time we have 2 different eddies, one called Kraken and the other one called Lazarus. And you will notice the separations shown in the 4 panels above. You'll see these swirls here. This is an anti-clockwise flow under the edge of the front, and we get another one here, and similarly another one here. Generally, you see them just displaced from the position of separation. And again, if we look at this one, this is the averaged energy for each of these boxes. So the black is for under the loop current, blue is to the northeast, and the red is to the northwest. And what we see is just prior to the first separations, we see these large peak in fluctuation energy, eddy kinetic energy, under the loop current, less so to the northeast and northwest. But then later on, we see a peak in the northwest much later in the cycle. Again, and then once the eddy has departed, you see the energy in the bottom waters in all 3 positions all decreases, becomes quite low, and then as the next eddy, Lazarus, begins to become unstable, you get another big increase in eddy kinetic energy under the loop current. So we have 2 separate sets of measurements, moorings and floats, that show the same features for essentially 5 different eddies, eddy separation events. So we want to know what the distribution of eddy kinetic energy with depth looks like. And look at this plot first. We have 2 more. A3 is from the loop current study, and similar mooring at L4 was from an earlier study of the northern Louisiana, Texas slope area. And if we decompose the currents into profiles, we can explain a large amount of the variability with very few modes, or what we call modes, statistical modes. In this case, 82 and 15%, 90%, 6%. The blue and the red are under the loop current. And what you see is an almost depth invariant current going from surface to bottom, and then it goes from 0, approximately 1,000 meters or so, and increases towards the surface to fluctuation. So you've got a surface intensified current there, and you get a similar thing happening at L4, except that the straight up and down mode here has become bottom intensified. That's a signal of what I'll talk about later as a topographic Raspberry wave. So if you integrate these currents up into a mean flow, which is the average over 2 years, one due to the barotropic mode, the depth independent mode, and one due to the surface mode for all the moorings in the loop current, what you find is that you have divided between mean flow and surface intensified flow along the Campeche bank. And as soon as you get into deep water, the depth independent mode becomes dominant. And you can see the mean flow mode begins to decrease, and so does the fluctuation mode, the surface currents. So you can see that from a 2 years average fluctuation energy, most of it goes into the depth independent mode, which means it goes all the way down to the bottom. And then you have to remember that part of the reason for this is that below the loop current, you still have 2,000 meters of water column. So anything, even though the fluctuations may be only 10, 15 centimeters per second in that water column, as against 150 centimeters per second at the surface, those currents are through 2,000 meters of water column, whereas in the surface layer, it's only in the upper 500 meters or so where you have the stronger currents. So this is a sort of hand-done animation is to show you something what happens. So this is for Eddy Hadal, and the solid line is a 17 centimeter sea surface height, which delineates the area of the loop current. The red arrows are the velocities from the moorings at about 100 meters. So when I go through this, you'll see you'll see them advance. So they're every 15 days, and the shape of the front is important. So you see the crest of what we will call a crest of a meander, and then a trough of a meander over the deep water on the east side of the loop current. So remember the 17 centimeter current is showing you where the flow is going, where the strongest flows are. It doesn't always quite correspond, but so the fainter line is the previous time, 15 days earlier. So what you need to look for here is that as I slowly advance them, you'll see that the crest and trough will advance towards the southeast as a propagating meander. So the next one, you can see that is moved further to the south. Again, it's moved further to the south, and again moved further to the south. Crest in the trough, and then it starts to straighten up again, and then lastly straighten completely out. So in this case, it did not produce a separation or a detachment. The loop current returned to its sort of extended static position. Okay. So what is happening? Well, this is basic geophysical dynamics theory, and it applies in the atmosphere as well as the ocean. And the analog in the atmosphere is the jet stream and its production of storms as it meanders across the continent. What you see is that the meander propagates. We have a trough and a crest, and underneath these troughs and crests, you produce a deep eddy, which we're calling a low, which means it's anti-clockwise cyclonic circulation, and just downstream of the crest, there is a high, which is a clockwise or anticyclonic circulation. And these, again, remember that the loop current only goes to 1,000 meters. These things extend through the whole lower water column to 2,000 meters of water column. So this is called the baroclinic instability. And the crucial point is that the high and lows are displaced from their corresponding surface layer troughs and crests of the upper layer jet. Okay, So this is from Kathy Donohue's work. And what you're looking at here is a sequence every 10 days of bottom pressure and sea surface height. In this case, the sea surface height is the solid contours, the filled contours, and the bottom pressure is the open contour lines. So what you can see here is you have a sea surface high. These flows are being filtered to remove the mean flows. The position of the loop current is shown by the solid line, the solid green line. So here you have a surface high and then a bottom anticyclone here. And you can see them intensify and move around the loop current in sequence. So they are propagating, they are moving around, and then we lose track of them when they move out of the array. So, you can see B, A, and B all moving around across the loop current. And it's this process that affects the separations. So try and make that a little bit clearer. Again, we have another very short movie. In this case, unfortunately, the schemes are reversed. So the bottom pressure is in the open contours. The bottom pressure is the solid filled contours, and the surface highs are the open contours. So again, you can see the displacement of the bottom relative to the surface. The surface, this is the bottom. This is the surface, this is the bottom. So the bottom always leads the surface, which is expected in a barotropic instability. And it's just a short, you can see them moving around in the sequence. It's very short. Do that again. It's really quite fascinating. So you see that both the surface and the bottom are not in phase. They're not the whole water column being reflected in the surface. You actually have two different circulations which are connected but are out of phase. Okay, so we can see this particularly well with the floats. These are blue lines in these are all at 1,500 meters. The reds are at 2,500 meters. So they're well below the depth of the loop current. And what happens is you're beginning to develop a meander trough here. This is towards the Yucatan Straits here. And these floats come in and start to go in an anti-clockwise direction, or a cyclonic eddy, and they tighten up. As they tighten up, the front 17 centimeter contour here gets steeper and steeper, and then breaks and becomes separation. So it's still doing a cyclonic. Notice it's displaced from the center of the trough, and once it's separated, floats all disappear. They all go off to the west. It's one of the problems with Lagrangian floats is they will go into a feature, stay for a while, and then disappear. You can track almost exactly when these floats go under the loop current. The water temperature will rise even at 1,500 meters. You will find that the temperature will rise by a few tenths of a degree as these floats move in and then move out of the trough. Okay, so that particular sequence was dense enough so we could analyze the currents in a sort of statistical way. So these are all those float tracks over a month period or a month and a half period that went into that clockwise, anti-clockwise circulation. And we can use the velocities of these locations to determine what the flows look like at this depth. So the black arrows are the mean flows for this period, and you can see they're quite strong, getting up to 20 centimeters per second over that, averaged over that month and a half period. So you can see how strong, and then any current at this depth will extend all the way up through the water column. So you can see that these kinds of flows can interact with the flow of the jet above it, and that's what causes the meander troughs to deepen and become eventually cause a separation. This is a nice example of just one float track. Starts at the green point and ends at the red point, but it makes 4 circuits of an eddy, again an anti-clockwise circulation, a cyclone, and it moves across an extended loop current. It didn't create a separation in this case, but it does show you that these deep eddies can move across the loop current, and you would expect them to keep going and do something out here. Notice that we don't see really any loops up in this region. So the fluctuations of the paths, the floats, are not really loop-like at all. It's only when they get into this region that they do. Okay. So whether the question is, where does the energy in the deep water go after a separation or an eddy gets separated? We know it decays. We know that we don't see it all the time under the loop current. So where does it go? And one of the principal ways we think it goes out is through planetary waves, which are called topographic Rossby waves, or TRW here, which transfer momentum towards the Mississippi Delta, but they don't transfer mass. They are a wave, not an eddy. So they don't transfer any mass towards the Western Gulf, but they do transfer energy. And so what happened here was that these 3 floats fluctuated backwards and forwards at a small angle to the isopath in where there is a reasonable slope on the bottom. The topographic Rossby waves require a bottom slope of the seabed for them to work, and you can see the fluctuations. And it was a very long period. They fluctuated backwards and forwards over 6-7 month period before being dispersed. So again, these are not these waves are not dispersing water particles. They're just fluctuating backwards and forwards. And you can see that the eddy during this period, while the loop current retracted, the fluctuations of the floats in this region is very low. These just sit around and almost do nothing in this region in the northeast of the basin, while the loop current has disappeared. So there is a very large change in energy from when the loop current is extended and becoming unstable to when it's not there. So, the big question is, where does that energy go? And one hypothesis is that they go into these topographic Rossby waves, and this is an almost perfect signal of waves being propagating through this region with actually a change in frequency. So if we look at them in a more detail, we can see these are 10-day sequences. The black dot is at the end of each sequence, and the color changes, from red to orange brown. And you can see that they move along. The blue dot is the middle of that ellipse I just showed you. So you can see that they move almost entirely together, hardly separating at all, come back, and then they start to change their direction and start to fluctuate across. This is not the whole sequence. So one of the characteristics of topographic velocity waves, the fluctuations are a small angle to the direction of the isobaths for very long period waves, and for short period waves, these are about 60 days or so, and then these are about 40 days, 30 or 40 days. The direction of the paths becomes more across the isobaths. So I think what we're seeing here is different wave trains coming into the region from different areas. So if we can ray trace these things, and this is from an earlier study where we have some moorings up here, and Louisiana State University had a mooring down here. And if you ray trace them, you can see that where you had high energy under the loop current here, it can propagate into the slope, and where we also show high energy below a very steep escarpment. There's an escarpment here marked by those two gray lines, which drops about 500 meters in less than 10 kilometers. So, the energy can propagate into the slope, and we postulate that it actually gets reflected back into deep water because we saw very little energy above the escarpment. And then this is a much slower moving wave, and it probably loses its energy as it comes in here. So you see a little bit of a bulge here, but it's nothing like as large as the bulge that comes in, the increase in energy you see here. So let's go back to the RAFOS floats, and what we see here is, again, the point out is high energy under the loop current and stretching towards the Mississippi Delta and the Sigsbee escarpment in this region. And this is the mean flow calculated from the floats by my colleagues. And you can see that there's a boundary current that runs along almost the whole of the basin, and it comes back into the eastern basin and forms a dipole where you have an anti-clockwise circulation here and a clockwise circulation here. Notice it does not go up into the DeSoto Canyon region. So you're seeing the black arrows are considered to be significant, the red arrows are not considered to be significant mean flows. This new picture of the deep circulation in the western, in the whole of the deep Gulf, seems to be related to this Eddy and TWRM. So the speculation is that we know we can see the generation of deep eddies under the loop current when it's becoming unstable. What's much less well known is whether we get the radiation from the loop current we appear to. The data is consistent with that, and it appears to be mainly in the form of planetary waves or topographic waves, which propagate towards the escarpment in the northern Gulf. And this is a schematic of what we think is going on. So the red and orange colors are the surface layer eddy scale circulation. So this one is the loop current. This is a separated eddy. This is an old separated eddy that's propagated into western hour that's been split into two. And then there's what's called a Campeche cyclonic gyre, which is probably wind-driven, a separate circulation feature in the Campeche Bay. And then the deep circulation consists of this boundary current, which runs apparently all the way around the Gulf, as according to the floats, and then gets wrapped up into a dipole here under an extended loop current. These again are mean flows, so this is a clockwise and an anti-clockwise circulation. And then I've represented the energy moving into this escarpment by this sort of blurred line. And there's a theoretical reason why we think the topographic Rossby waves can be rectified by the topography and generate a mean flow along a sloping topography. So we think that maybe the deep energy is one of the means that the boundary current gets forced. There are other theories and other reasons, which are sort of, it's probably more complex than this. Okay. So
hey, Peter. It's Abby. It's after 1 o'clock. How many more slides do you have?
Oh, just 2. Sorry.
Okay, perfect. No worries.
So this is just a sketch of the circulation from surface drifters by the Carter program. The GLAD study was run by University of Miami. And there's a separation of an eddy called Jumbo. All these surface floats, a large number of surface were released in clusters in this region, the red dots. And you can see you get quite a complex circulation just because you have a strong eddy out here. And you can see you have a anticyclone here and an anticyclone going up into the DeSoto Canyon. So it obviously also affects circulation over the slope. So that's basically my last slide. So loop current dominates circulation in the Western Basin. Loop current eddy detachments directly relate to instabilities of the meandering deep water jet on the east side. You get mutual amplification of surface and deep cyclonic and anticyclonic flows. Evidence of deep eddies radiating energy through TRWs towards the northwest. In the Western Basin, you get surface layer forced by westward and southward propagating shed large-scale eddies, loop current eddies. Deep anticyclonic boundary currents along the steep escarpments may be partly driven by radiating loop current TRWs impacting the Sigsbee escarpment. Okay, questions?
All right, thanks so much, Peter. We had 3 questions come in during your presentation, and we'll get those answered. And for the ones that we can't get to, I will share Peter's information with everybody who's attended the webinar. So the first one is from Catherine Weathers. Are the In-Situ data available for others, specifically the Yucatan Channel moorings?
I'm not directly sure about the Yucatan. All the Department of Interior data is available. So that's the RAFOS floats and the deep water moorings, bottom moorings, PIES data, and the transects across the Campeche slope, which were partly funded by BOEM, are all available.
Great, thanks so much, Peter. And the next question is from Danielle Westhaver. Does the formation of a loop current eddy and the energy it produces cause the Gulf Stream to slow down?
That we don't know, I would say. We don't think so, because what comes in through the Yucatan transport as volume transport must go out the Florida Straits. Otherwise, there'd be huge fluctuations in water level in the Gulf of Mexico, and that doesn't happen. So there may be short-term fluctuations, but anything longer than a few days is not going to affect them. So what comes into the Gulf of Mexico must go out, and the Gulf Stream off Miami, say, also has components coming from the Old Bahama Channel, the Northwest Providence Channel. So it's not. what you measure there is not exactly what you see coming out through the Florida Straits.
Understood. Thanks so much, Peter. And then one more question. How are the loop current eddies named and who names them?
Okay. Yes, I'm sorry, I meant to mention that. Yes, there is an industry group, an industry consortium, and one of their contractors actually called Eddy Watch, and they name the eddies as they detach. Sometimes they get it wrong, but most of the time, and they're named alphabetically, obviously. But who chooses the names of the eddies? I'm not quite sure.
Thank you, Peter. And then, do you have time for one more question?
Sure.
Jose Valencia, what kind of interaction occurred between the western side and the detachment of the loop current eddy in the eastern?
Well, that could be complicated, and we don't really understand it. What we see these small scale frontal eddies running along the slope, and they have to be formed by some kind of instability. But the water depth is limited there by the slope, to 500,000 meters. And when they get into deep water, they propagate around the loop current as you would expect. And once they get into deep water, they seem to disappear or become much weaker, decay. So we don't, at the moment, think they play a major role in the detachment process. So major thesis that we came up with from the loop current study was that you have to have the baroclinic instability and the deep eddies form to get a detachment. So it's a large scale instability process, and is probably not primarily related to just the surface flow meandering. Meanders have to get their energy from somewhere, and they get it from the mean flow, and then when the deep eddies form, they mutually reinforce themselves.
All right, thank you, Peter. So we are going to stop the questions, seeing that it's 1:07, and I'm going to take over as presenter. If we did not get to your questions, I'm about to share my screen, and you'll see Peter's email address, peter_hamilton@ncsu.edu. Please email him. He'll answer any questions that you have, and you can also email communications@socorro.org. Peter, thank you so much for the great presentation, and thank you guys for attending and asking such great questions.